thank you to the organizers for the opportunity to speak, and especially for being flexible and letting us change the order around a little bit. So I'll be giving the longer talk, and then Pengzi will be giving the 45-minute talk in the second slot. Okay, so there's a few parts. The first part, I'll just be reviewing some things about capacity in the smooth setting. The second part will be on low regularity capacity, and the third part will be making the connections with scalar curvature and general relativity. So just the definition, starting with compact subsets of Rn, the capacity is defined by minimizing the Dirichlet energy of test functions that equal 1 on the set, and they are compact support or go to 0 at infinity, okay, with some normalizing factors. So if the boundary of the set you're talking about is regular enough, then you get a minimizer that's a harmonic function outside of the set, which is a useful way of computing the capacity in some cases. There's a couple physical interpretations of capacity. Usually what you'll hear is from electrostatics. It's the maximum charge you can place on a conductor to maintain a voltage difference of 1 unit between the surface and infinity. Something that I like a little bit better, it just is a little bit more tangible, is if you have a body immersed in a medium. So you're standing outside on a cold day, for example. The capacity is the rate of change of, it's the amount of heat you have to pump into the system to maintain a difference of 1 degree. So it's basically it's basically if you're out on a cold day, you want to minimize your capacity if you're trying to stay warm. Okay, so just a couple examples. The capacity of a ball is just the radius of the ball to a power depending on the dimension. Capacity shares some properties with volume, like it's monotone. Larger sets have larger capacity. And then this will become relevant with the general relativity discussion at the end. Actually, there's basically an isoparametric inequality for capacity. So it says the capacity is bounded below by the volume once you scale everything appropriately. So nowadays, this is often called in the literature the isocapacitary inequality. And of course, please interrupt me with questions. I can only see a couple of the screens at any time, so please just speak up if you have any questions. The capacity generalizes readily to Riemannian manifolds. All you really need is magnitude of the gradient. You need the volume form, so the same definition is in play. Often the set we're looking at is just the boundary of the manifold. Let me give a few examples just to give some intuition on capacity. So for example, if you've got a manifold that's maybe Euclidean, but then you have a long neck. So you've got maybe a spherical boundary. So that's the boundary. You have a long neck, some length L, then the capacity, you can make the capacity go as 1 over L. So what you can do is use a test function that's just interpolating linearly between 1 and 0 on the length of the neck. So if something's getting sunk down a deep well, it'll generally have small capacity. Another example, if you don't have a long neck, but if you have a thin neck. So if you have some set, let's just make some set K. It could be any set inside this bubble here. If you have some thin neck here, and say the space opens up to something like Euclidean space at infinity, then you can make the capacity of this will be very small. Okay, you just make your test function do its transition between 1 and 0 when you're close to that small neck. If you have a cylindrical end, for example, or just more generally a small end, something that doesn't open up very quickly. So here you could just have maybe this could be just an S2 cross array. Then if your set K is the boundary, then the capacity is actually always equal to 0. Actually, not just of the boundary, the capacity of any compact set would be 0. Just basically the end doesn't open up fast enough to have a non-zero capacity. You can again use test functions that just slowly interpolate between 1 and 0. Okay. Oh, one other example I want to give. If you have some manifold, and you want to talk about the capacity of some set within it. So this is your M, you've got some set K. If you change the metric outside of K by maybe removing a small ball and then pasting in what are sometimes called, especially in a GR context, gravity wells, or you put in some long, a tentacle might be a better word, or just some long finger. If you do something like that, the capacity is largely insensitive to that. If you put in a finger like that or a tentacle, there's no reason for the capacity to see that, because there's no advantage to the test functions changing very much on those tentacles. So the capacity doesn't care about things like that. If you do change the metric at all outside of your set K, then you are in fact changing the capacity though. So it's non-local. You can, I mean, that should be clear from the definition, but if you think of the definition as having, as being minimized by a harmonic function, if you change the metric somewhere, that's going to change your harmonic function everywhere. It behaves in a predictable fashion if you globally make a uniform change to the metric, because if you can estimate the metric above and below, then you can estimate, test functions, gradient, the volume form above and below. So the capacity is continuous under global changes, but it's actually not continuous under C0 loc changes, for example. This is just an exercise, this isn't not hard to show, it really just follows from the definition. If you have a sequence of metrics converging uniformly on compact sets, then you can easily show a semi-continuity of the capacity, upper semi-continuity. In other words, the capacity can jump up, but it cannot jump down according to this. And likewise, you can show this for pointed C0 Cheeger-Gromov convergence in case the metrics aren't all on the same manifold. It's simple to give an example where you actually get this jump in capacity. You could do an example, it's probably the simplest thing I could think of, where you have a Euclidean ball out to some radius I is just an integer. You have some ball, here it is just a flat ball, or even a two-dimensional disk if you want, and then your manifold changes so that it then opens up to have a cylindrical end, and you can round out the corners so you get a smooth metric if you want to. But in this case, if this is your space Mi, then because of the cylindrical end, the capacity of any set is going to be 0 for each I. So let's fix a specific K there. We could say a capacity with respect, capacity and Mi of K. 0, that's just forced by the asymptotically cylindrical end, or the cylindrical end. But Mi converges in C0 loc to just Euclidean space. Just because that ball is getting bigger and bigger with I. In Euclidean space, you could easily have a set like a ball, for example, with positive capacity. So this is showing that you can have a capacity jump up due to changes in the end behavior of the manifold under your sequence. Okay, so just to make some connections with what I'll be coming back to later, capacity has shown up in a number of ways in the last couple decades in the study of scalar curvature and mass and general relativity. I'll say more about some of this at the end, but Bray used a mass capacity inequality that he proved for asymptotically three manifolds with non-negative scalar curvature in his proof of the Penrose inequality. This led to a number of related inequalities involving mass and capacity. Again, the connection here with scalar curvature is that these all require non-negative scalar curvature. A local result is that just like you can detect scalar curvature through volumes of small balls in a Riemannian manifold, there's a result that you can actually detect scalar curvature by the behavior of capacity. Technically, it's the relative capacity of concentric balls. The last part about capacity on the large scale to detect mass, that's really what I'll be talking about in the third part of the talk. And then I'm also excited to mention this result of Pengzi that he'll be talking about in just an hour or so, New formulas for mass and capacity in an asymptotically flat manifold, new monotone quantities, and new proofs of the positive mass theorem. Okay, so I mentioned the semi-continuity of capacity with C0 convergence or C0 low convergence. The first question that's going to form the motivation is, how does the capacity behave with coarser changes than that? So something that doesn't even respect metric tensors necessarily, so not even C0 convergence.
Jeff, may I ask you a question?
Sure.
There is also there is a notion of capacity also in symplectic geometry. Is there any connection between these two? I mean, we can discuss this later if there is no short answer to this.
Can I make a remark? Can I make a remark? It's incorrectly used terminology. In symplectic geometry, it has spectrum or length. They call it capacity just because it sounds better than width, but actually it's width. It has nothing to do with capacity. It's completely different invariant and behave like width or like spectrum, but not as capacity. It has no additivity to it in intrinsic. So just wrong terminology, which I resist tremendously. Very confusing. It's not capacity. It's very different type of invariant. Okay. Capacity is used because the word sounds nice. Period. I think it's the wrong way to make terminology. So.
Okay. Thank you for that.
I'm really kind of very much against it here.
Okay, great. So, so if we're wondering about coarser convergence than C0, there's a number of candidates you could ask about. The theorem that's going to motivate us is a theorem on the semi-continuity of eigenvalues, which share, some similarities with capacity in that you're minimizing Dirichlet energy. This result followed earlier results on Gromov-Hausdorff convergence on the semi-continuity of eigenvalues. This result here of Portegies studies convergence for volume preserving Sormani Wenger intrinsic flat convergence. So I'll be going into more of the details on that shortly. But if you have this notion of convergence, which is much weaker than C0, then you get a semi-continuity result of the eigenvalues. So in light of this theorem, we'll refine the first question to ask, is capacity upper semi-continuous for VF convergence? Since the spaces we're dealing with are non-compact, we'll be talking about pointed convergence. So that's one of the questions we'll want to answer. The second one is, since capacity itself has some connections with general relativity and scalar curvature, does the semi-continuity result have anything to do with those subjects as well? So that's really the two main sources of motivation. So that leads into this next part where we'll be talking about capacity in the low regularity setting. This is joint work with Raquel, Perales, and Jim Portegies. So I'm just gonna, I'm not sure of everyone's familiarity with intrinsic flat convergence, so I'll be going through this pretty quickly, but recalling a number of the details. So this starts by looking at currents. So currents classically are functionals on differential forms on a manifold. Ambrosio and Kirchheim generalized this to currents on a metric space. They replaced the idea of T acting on a differential form with T acting on tuples of Lipschitz functions, which makes sense on a metric space. There are a number of properties they must have besides multilinearity, but one of the properties is finite mass. Mass, by the way, that's just speaking of terminology, this is a little bit of a clash in that mass in measure theory is a different thing from mass in general relativity, but both of these words are going to get used here. But essentially, this is saying finite volume. That's not going to work for us because we want to study spaces like Euclidean space, for example, and much more general ones which have infinite volume. So we use local versions of these currents. A theory on these was developed by Long and Wenger. It's a similar idea. You look at multilinear maps on Lipschitz functions. Lip B, these are bounded Lipschitz functions with bounded support. And then these are locally Lipschitz functions. There's a couple technical properties they need to satisfy. There's a continuity property and a locality property. I'm not going to really do anything specifically with those, but there are a couple properties there. One of them that I do want to mention is the mass of a current. So these eventually want to lead up to the definition of locally finite mass. So you can talk about the mass of one of these currents by just trying to maximize it with with the natural constraints. If you have an open set, you look at functions f that you can plug in, finite sums of them that add up pointwise to at most 1, and you use your pi i's that you plug in to have Lipschitz constant at most 1. You look at functions that are supported in your open set, and you try to maximize that quantity. If you're dealing with
why ask a question? Because there is different normalization. It's for non-Euclidean space, there are many ways to normalize volume. So in Minkowski space, what you call volume. So which one is chosen here?
So you mean like with a metric signature in Minkowski space?
Yeah, for example, if you apply it there, what kind of which one volume you get in this case? What you call volume? Because there are many normalizations.
I would have trouble with that because you're not going to get a metric space in the usual sense because you'll have 0 lengths. So I think that would give some trouble for defining Lipschitz functions and everything. But this should agree with which is the usual, like in the Riemannian.
No, but there is no. The whole point. Usual, there are many usual. When you go to Minkowski, all usual go in different directions. For different purposes, you use different kind of volumes. And then if you want sharp inequality, it's crucial. For scaling curvature, I think it's crucial to have well-balanced normalization of the volume. What you call volume of unit ball in the Minkowski space in 2 dimension, what you call volume. And we can postulate volume is equal just, pi squared, right? Or you can say something else.
Mm-hmm.
And they're all different. And the different by constant which goes to infinity as dimension grows.
Okay.
So which one you choose here in this theory?
So I'm not using the word volume here. I mean, this is the definition of the mass here. So this, I think, should be unambiguously defined in a metric space.
But mass is, this terminology you said don't care, right? The question is, if you use this definition of mass or volume, coming back to the Minkowski space, what you get?
That's a good question. I would have to think about that.
Okay.
Yeah. Sorry, I don't have an answer to that. The thing that's confusing me is just if you're doing Minkowski, then you have you don't have a usual metric space, so that doesn't seem like it would quite fit into this. But
we speak of different Minkowski space. I mean space with a field symmetric. I'm not speaking in definite metric. I speak of positive definite Minkowski space.
Okay.
Minkowski metric or Banach metric, if you want.
Gotcha. Okay, I see. I don't have an answer to that. Let me think about that. Okay, I apologize. Okay. So the mass, once you have this definition, then you can define it on arbitrary sets just by regularizing from the outside. You just minimize this quantity on open sets that contain your set. This gives you an outer measure. So we'll be using this outer measure T. It's a Perales measure. We'll be using that extensively in some of the definitions. Once you have that, you can define a current with locally finite mass. You need 2 things. You need it to give a finite result on bounded open sets, and then you need to have this nice property where you can find compact sets inside of your open set. Oh yeah, typo here. This should be a C inside of U. So a compact set inside of U such that the set difference has as small of mass norm as you want. Okay. So these are the kinds of objects we'll be working with. Specifically, I won't give all the details here, but just like with classical currents, they come in many varieties, integer rectifiable, integral currents. There are nice analogies of these to metric spaces that were developed by Ambrosio and Kirchheim, and then those can be generalized to this local case as well. So locally integral currents will be integer rectifiable currents where their boundary is also integer rectifiable. This is just an analogy with usual integral currents. Okay, so building up to the definition of a local integral current space, we need the canonical set. This was used by Sormani and Wenger in their definition of integral current space. It's a way of measuring where an integral current or where any current lives within a metric space. So it's the sets of it's the points where there's positive lower density for this measure. It's a smaller set than the support. The definition, this will really be the key definition of in our theorems, is a local integral current space. This mirrors the Sormani Wenger definition in the non-local case. It's just a metric space with a locally integral current. The current's defined on the completion, but you need the canonical sets to actually give you the to equal the entirety of the original set. So a good example of this, if you're more differential geometrically inclined, is just your fallback example is a Riemannian manifold. So a complete Riemannian manifold, connected so you get a distance function, oriented so you can use your integration to define your T. These will give examples of local integral current spaces. If you restrict one of these local spaces to balls, then at almost every radius it forms, it'll have finite mass and it'll form an integral current space. This follows from a result of Sormani, which uses a slicing theorem. Just a brief review of intrinsic flat convergence. So this is a build up to the definition of pointed intrinsic flat convergence, but just to recall some of the details here. If we have a sequence of integral current spaces, they converge to another integral current space of the same dimension in this F sense. If you can embed them into some common complete metric space Z. So you've got this one, this is your phi of X. You've got some phi of Xi here. So if you embed these into a common metric space Z, once they're in there, then you can compute the flat distance. The flat distance really looks at, the deficit and their boundaries, and then you're trying to fill in between them as much as possible. You're trying to do that as efficiently as possible. This is just modeled on the usual flat distance for currents in Rn. And intrinsic flat convergence means you can do this in such a way so that that flat distance goes to 0. In general, you can have mass drop, for example, through a cancellation effect, but you can have an additional requirement of volume preserving. So if the total masses are preserved, then we call that VF convergence. Okay, this is the type of convergence that was used in that semi-continuity of eigenvalues theorem, for example. You can also have convergence of points. So if you have points in your Xi's, they converge to a point in the completion of the limit space. That just means you can find these embeddings as before, where the images of those corresponding points converge. So that'll show up in the definition of pointed intrinsic flat convergence. We have that here. So now we have a sequence. Let me just draw attention to the differences. It's a local integral current space. So it has only locally finite mass, converges to one of those same types of objects. And now the pointed sense, pointed, you have to specify points. And it's just what you would expect. If given any radius, you can find a potentially larger radius so that the restricted integral currents, those restricted integral current spaces converge in the intrinsic flat sense. And then also if you have the points converging as we defined in the previous sense. So it's a natural notion of extending intrinsic flat convergence to the pointed case. Similarly, you can define VF convergence where you would just require VF right there so that you're not having a mass drop. Okay. So with that, we have a lot of the setup for being able to talk about the theorems on low regularity capacity. The only thing we're missing is a definition of capacity and low regularity. To do this, you need to be able to talk about the Dirichlet energy that you're trying to minimize. So you really need to be able to talk about derivatives of Lipschitz functions defined on one of these spaces. This is modeled on the same definition that Portegies used for defining the eigenvalues in an integral current space. So let's say we have one of these integral current spaces and we've got a Lipschitz function with bounded support. We want to say, what is its Dirichlet energy? The strategy here is to embed your metric space into a Banach space. X, there's a result that it's countably rectifiable. that's basically the measure theoretic version of being a manifold. So you can embed that into this space. Because of that structure, you can define a tangential differential on the image of X when it's embedded in the Banach space. So this is a way of taking the derivative. This is not defined everywhere, of course, this is defined almost everywhere. But you can define a tangential derivative. That could depend on the choice of embedding. So, but the magnitude does not. You can talk about the magnitude. This is really just generalizing the norm of the gradient to this much more general case where we're embedding everything in when we're working in a metric space. Okay, that as you would certainly want to be true, that is always bounded above when it exists by just the Lipschitz constant of the function. So it's finite in particular, it's bounded. Once you have that, then it's a simple matter of going from there. You have this function, you can integrate it, we'll square it and integrate it to get the capacity. You integrate it with respect to the volume measure. Okay. Thanks, Christine. I'm just glancing at your note in the chat here. Okay. Maybe we can talk about that a little bit at the end. So you can define the Dirichlet energy by doing the norm of this tangential differential with respect to this T measure. If you wanted to, we didn't do this, but if you wanted to, you could make this into a P capacity and do a similar thing. And then once you have that, it's defining capacity is analogous to how you would do it. You just minimize this on Lipschitz test functions that equal 1 on K. Actually, for technical reasons with a lot of these capacities and metric spaces, it's nicer to require that your function is 1 on a slightly larger neighborhood of K. So that's actually what we do. It gives the same value in Riemannian manifolds. I should mention there are many other, well, I don't know about many, but there are other ways of talking about capacity in metric spaces. This is one that works well on integral current spaces. This has received some attention in the analysis literature in the last decade or so. I'll refer to a couple. These are both very nice books that go over this in a lot of detail. One of these approaches is based on defining Sobolev functions in metric spaces or metric measure spaces. Another one's based on weak upper gradients, but there are a number of ways of talking about capacity on metric spaces that I just wanted to make sure I mentioned. Okay, with that background, we can now state the first of the main theorems. Remember, we're trying to generalize this semi-continuity of capacity result to a low regularity setting. So here we have convergence of local integral current spaces. They converge in the pointed volume preserving intrinsic flat sense. We have points in the spaces, and the P, notice the P here is in X, not the completion of X. So we actually do have a point in the limit set that this is converging to. We need the ball to be compact in the limit space. If you have that, then you get this, this same upper semi-continuity of the capacity. Okay, so the capacity can jump up when you pass to the limit, but it cannot jump down. I'll give a couple examples of this now. And then we'll do some examples, then we'll talk about the next result. So basically what we're saying is the capacity should be able to jump up, but not down. I'll give two kind of more simple examples and then one that's a bit more interesting. One thing to note is you could already see this capacity jump in even just for smooth manifolds with smooth convergence, just by the end behavior changing at infinity. These examples don't involve changes to the end behavior. These examples are really, the interesting stuff is happening localized on a bounded region. So with this example here, you can literally just think of these as subsets of R2 embedded inside of R3. So this is just a flat plane with a disk cut out of it. The disk is cut out of it and slid down. Let's say they're distance 1 over I apart, so they're getting closer and closer together. Xi is the union of those. Let's say they're oriented the same. And then that gives you a local integral current space, just doing integration over these two sets. So that gives us a local integral current space. We could put all the PIs. If we want PI, just center that there, center your P there. And what's happening is this converges in the volume preserving intrinsic flat sense, or the pointed sense, to just a nice flat Euclidean R2. So those pieces kind of come together. The limit space, you could have the capacity of K certainly positive. Just choose, a ball, for example. Over here on the left, the capacity of that set K could be just a ball, again centered at pi of small radius. Those capacities are always 0 because they lie in the set just lies inside a connected component. You could use your test function that's just 1 on that component, 0 on the other component. That's technically Lipschitz, so you just get 0 for the capacity there. So this, you can get the capacity being 0, 0, 0, 0, 0 for the sequence jumping up. If you don't like how this is disconnected, you could join the disk up to the rest of it with just a thin bridge or a thin ribbon. You might have to make it very thin as you do that, but as you connect those, you'll get capacity not 0, but you'll get capacity that's going to 0. So you can still see that jump, and it would still be connected. Okay. The next example will be similar to this one, but it's to demonstrate that you can get a capacity jump going the wrong way if you don't have the volume preserving convergence. So with this one, again, everything could be happening inside of R3. So this is just a flat R2. The trick here is that the two pieces, there's this annulus up top that's oriented one way. Integration is one way, and then integration the other way is down. So they have opposite orientation. Again, let's let them come together. So as I goes to infinity, these are, coming together. They merge and you get a cancellation. So it converges in the intrinsic flat sense where you get a cancellation and then you just have a missing annulus there. It's just not there. So in this case, the capacity of the ball, that, let's say R is just some small radius there, some R, the capacity of that is 0 because again, it lies in a connected component. But over here, the capacity PIR, these would all be positive. So if you have a small ball there, okay, they don't care that there's an annulus sitting above it. The capacity doesn't see that. Okay, so but notice here, this goes the wrong way, but this is F convergence. This is not VF. You have some mass loss because of the cancellation effect. Okay, the next example I think is a bit more interesting. This did not appear in the posted version of our paper, but let me go through and give an idea of what's going on here. So this is more interesting. It uses the sewing developed by Basilio, Jauregui, and Sormani. So to construct this example, it'll start by looking at a rotationally symmetric metric. So let's look at a rotationally symmetric. Let's do it in 3 dimensions. So you're warping an S2. Let me show you what F looks like. So what this looks like is you've just got a, let's say for 0 to 1, the function f of s is just s. So that means it's the Euclidean metric up through radius 1 and actually just a little bit past 1 as well. And then at radius 2, it is again like that, except it's s minus 1. It's just that same line, but shifted. So that means outside of radius 2, it's just the complement of a Euclidean unit ball. Okay, that value and that value are both the same. They're both 1 for f of s. So it's a Euclidean ball and then a Euclidean unit ball complement. Between them, we make the metric very small. So we're joining these two, we're joining these two regions with a bridge where the metric gets very small. Okay, so this region here, we'll call this the bridge region, everything between s equals 1 and 2, and let's say that's about epsilon, that distance there. Okay. One of the things you want really is that you want the bridge to have a very small volume. Okay, so you can arrange that. So a diagram here, what this could look like is we've got, let me make it a little bigger. And that's going to be s equals 1. That's going to be s equals 2. So let's label those s equals 2, s equals 1. So s equals 2, keep in mind that is a unit sphere because of the value of the function there. This region in here is the bridge region. It has very small volume. Also, it's a very small function there. That's one of these small neck examples. So this will have, so anything in here will have small, anything inside here will have small capacity as well, because there's that thin neck joining them. Okay. So this, maybe that's our set K. Okay, so that's the starting point. Now this converges, but not to Euclidean space, because these two spheres s equals 1 and s equals 2, those are separated by distance 1. So even though you have this collapse in the middle, the limit will be some disconnected space. But what you can do is bring, you can kind of bypass that bridge, and you can bring these two spheres at s equals 1 and s equals 2 closer and closer together. So take a point on the first sphere, look at the corresponding point, the same angular coordinates on the other sphere. What you can do is cut out a small ball. Cut out a small ball there. And then you can join them with a small, you can identify those two spheres you cut out or join them with a small bridge between them. Okay, that's basically creating a shortcut from s equals 1 to s equals 2. This is really the heart of this sewing construction. And then you don't do that at just one point, you do that at more and more points as epsilon gets smaller and smaller. So you cut out a ball, and then you join those together. So this space I'll call m sub epsilon. It's this space that has this small bridge, this bridge of length 1 between them that's very skinny, but then it has all these shortcuts in it that are basically gluing this unit ball to the unit ball complement there. So this should actually converge in the intrinsic flat, in fact, the volume preserving intrinsic flat sense, to just Euclidean R3. Okay. So you have to be a little bit careful to make sure the capacity, you still want the capacity to go to 0. So you want the capacity of m epsilon going to 0 as epsilon goes to 0. And this is as epsilon goes to 0. You want that to stay small. So as you do these necks, you have to make them very narrow so that you can still estimate the Dirichlet energy of a test function and get a smaller and smaller result. Okay, but this shows a capacity jump because you can show the capacity. Sorry, this is the capacity of K in the space m epsilon. So I should have written it that way. So that goes to 0, but here K is just some set in the limit. It'll just have some positive capacity. Okay, so this is a jump in capacity for a different reason than change in the end behavior at infinity. So it's kind of lucky that you can get a result like this, because you have, on the one hand, you have a capacity jump due to end behavior at infinity. On the other hand, you could have a capacity jump due to just the coarseness of intrinsic flat convergence. But fortunately, they both go the same way, which is why it is possible to get a result.
Can I ask a question, Jeff?
Yeah, sure thing, Brian.
I'm confused. Maybe I missed some subtle thing here, but why isn't it converging to Euclidean space with like a sphere attached to a point when you do this?
Okay. Oh, you mean like a sphere that's like tangent to a point, something like that?
Yeah, because I thought the bridge is like being pulled to a point or something.
The bridge stays length 1. So the bridge stays length 1. So the neck's actually getting smaller and smaller. So without doing the sewing, it would actually converge to 2 separate pieces. It would converge to a ball complement and then a separate ball that's a positive distance away from it. By the sewing here, you're basically taking a Euclidean ball complement and you are sewing a Euclidean ball into that. You're basically just filling in that hole.
Okay.
Yeah, so maybe I'll draw the before you do the sewing, I'll draw it more geometrically rather than just with this schematic here. So so this is what I'm calling S equals 2. Down here, you've got that S equals 1 sphere, and they are joined by this bridge that's some very long, or not very long, very skinny neck like that.
Yeah, thanks.
Yep. Okay, so that's another more interesting example than those other couple. Okay, so the second main result uses instead of just balls are kind of limiting in that, you know, they're very specific sets. This second result is generalized so that you look at Lipschitz sublevel sets rather than just balls. Balls would be a special case of that. So assuming for the moment you can embed all your xi's and your x into a common Banach space with isometric embeddings, here's a way to take a region in your limit space and turn it into a sequence of regions in your converging spaces. So the general approach is to write your compact set in your limit space as a Lipschitz sublevel set. You can always do this by just using, for example, the distance function to that set. You can do it more generally. For sometimes you could use a signed distance function if you want something more interesting, but you just want your set to be the points where u is non-positive. Then you can take if you've embedded onto a common space, you can define u inside. You can define u on the image. Let me draw a picture here. So this is phi of x. K is some compact set. K is some compact set there. This is the set where u is non-positive. Then you can extend u to a global Lipschitz function on the entire Banach space, and then you can look at a Lipschitz sublevel set inside of the space xi, or here as I'm drawing it at the image, phi of xi. So for example, you could, if you're using a sign distance function, you could look at a level set of everything less than 0. You could get something like, so this green set here is where capital U is less than or equal to 0. And then all we're doing is we're defining this corresponding region to be the part where is the part that you get in the image of the other space. So that right there is what I'm calling the Ki. So this is just a procedure. It's not canonical. It depends on the embeddings. It depends on the embedding space, but it's a way of getting regions in your converging spaces that somehow correspond to your region in your limit space. Okay. These, if you don't want to just, if you want a little more flexibility, you can do UI is less than or equal to numbers that are converging closer and closer to 0. But this is really what I mean. It's a way of extending balls to sublevel sets and still talking about how sets in the sequence somehow correspond to sets in the limit space. The second main theorem is a version of the first theorem where we're allowed to use, where we're using these corresponding regions rather than just balls. The reason there's a technical hurdle here in that Sormani and Wenger proved this nice theorem. You could call it a common space theorem. It shows when you have intrinsic flat convergence, you can embed the entire sequence into one common space where you get flat convergence. That's not so clear in the pointed case or the local case. So we need to actually use a theorem that has a technical hypothesis that must be satisfied. So it's a similar statement before. We have these integral current spaces that are converging. The one technical hypothesis is that there has to be this bound on the boundary masses. I'm not too concerned about that because in a lot of interesting cases, you might just have that easily satisfied when the boundary is just 0 anyway, just boundaryless spaces. But if you can do that, that allows you to, let me skip down here. That allows you to use, with that hypothesis, you can use this compactness theorem to produce a common space where all these local integral current spaces embed simultaneously. This is a theorem of Long and Wenger. But what it's saying is you might have to pass to a subsequence to do this, but you can define corresponding regions and you still get this upper semi-continuity of capacity. Okay, so in the interest of time, I think I'll go ahead and move on forward to, actually I was pretty much there anyway. Move on forward to the part that makes some connections with general relativity. So to summarize at this point, we have a definition of capacity in metric spaces essentially, and we have a semi-continuity result. So just some brief background here. This is more the setting that Pengzi will be talking about in a little bit. Looking at asymptotically flat 3 manifolds. So these are, this is everything's, we're back in the smooth world here, everything's smooth. These are manifolds where the metric tensor decays to the Euclidean metric in a precise sense at infinity. The significance of those decay assumptions is that you can define the ADM mass. So physically, this is, you can think of this as the total mass, where mg is a space-like hypersurface in a space-time. So this is a geometric invariant that has this physical interpretation as mass. So again, we're using the word mass for 2 very different things in this talk. This is the physical one. There are a number of ways to understand mass. Just going back here, the definition relies on derivatives of the components of the metric tensor, so first derivatives. So as it's written, this is not a very good definition for dealing with low regularity spaces or low regularity convergence. So there's been some interest in trying to generalize this to spaces that are less smooth. A well-known approach, the most well-known approach to this is Huysken's isoparametric mass. This definition here has nothing, it doesn't use the metric tensor explicitly. It just uses volume. So that there is the volume of a compact set. This right here is the boundary area, or technically the perimeter. And those are the only metric quantities that show up here, volume and perimeter. What you're doing is you're going out to infinity with an exhaustion by compact sets. You're looking at volume minus area to the 3/2. You're trying to make that as large as possible. You're maximizing at infinity. Really what you're doing, if you think about it, is you're trying to minimize area with respect to volume. So you're really trying to find isoparametric minimizers out near infinity. And the claim by calling this a mass is that it should have something to do with this, this general relativistic definition of mass. Okay, but the advantage here is that it doesn't depend on as much information, doesn't appear on, it doesn't depend on derivatives. It's easy to check you get 0 because you can just use the isoparametric inequality that gives you, the isoparametric inequality gives you that inequality. If you use an exhaustion by balls, if you choose just larger and larger balls, then you get an inequality the other way. With a little more work, you can show it gives the correct value in the Schwarzschild metric, which is really the the gold standard. If you want to call it a mass, you really should get the correct value in Schwarzschild. Huysken proposed that it should actually be the same thing as the ADM mass when the latter is defined. And because the isoparametric mass is defined in more general settings, when you don't necessarily have derivatives, it would then be a generalization of the ADM mass. That is known to be true. One direction was observed by Pengzi to follow from results of Fei and Shi and Tam on large spheres and asymptotically flat manifold. The other direction is a bit more subtle. This requires non-negative scalar curvature, but you get an inequality for the other direction. The result here with Lee, this builds on ideas of Huisken and really rigorizes his approach to studying this. The other approach here I'll mention, this is a different idea. This is really trying to get a handle on what the isoparametric minimizers are at infinity to compute this. But the point is, this isoparametric mass is a low regularity stand-in for the ADM mass. Inspired by that, there's a definition. You might wonder, well, there's a isoparametric inequality that forms the basis for Huisken's mass. There's also an isocapacitary inequality where the capacity rather than area is bounded below by the volume. So the question is, can you also use capacity and volume to define mass in general relativity? So this leads to this definition here. We can call it, I'll just call it MCV, the capacity volume mass. It's completely inspired by Huisken's definition. You take a soup of a limb soup and you're trying to make the volume as large as possible relative to capacity when you're far out in the asymptotically flat end. Okay, so the normalizing factors and everything are just so you get the correct value in test cases. It's not hard to show that this gives you the correct value in Euclidean space. Again, the isocapacitary inequality gives you one direction. Just using balls as your exhaustion gives you the other direction. One thing it's worth pointing out that if you look at just this expression without taking the limb soup, the volume depends on everything inside the set Kj. The capacity depends on everything outside the set Kj. So at first it looks like this depends on the entire global geometry of the manifold. But if you actually optimize at infinity, this capacity value mass only depends on what's happening at the end. That's really a bare minimum that you would want in a mass in general relativity, just to depend on the end behavior. Okay. Let's see, maybe I'll skip through this. These are just some calculations you can do to test that you seem to get the right value in Schwarzschild. If you calculate the volume radius and the capacity, you can see that they're different. They both involve a radial term, but the difference cancels the radial term and you get a 3m over 2 minus m over 2. So you can kind of see you're picking out a mass term from that. You want to know, though, that it gives a correct value in Schwarzschild and other cases. So there's results in these directions to show this is a reasonable general relativistic mass. On the one hand, you get an inequality. You just need non-negative scalar curvature outside of a compact subset. That tells you this capacity volume mass is at least as large as the ADM mass. That's the easier direction. I should mention that uses a result of Ray and Miao that Pengzi might mention a little bit later from 2008 on estimating capacity using inverse mean curvature flow. The reverse inequality is not known in general. It's known if you look at exhaustions that are balls, that you're not taking arbitrary exhaustions, but you restrict to balls, or if you consider a nicer class of asymptotically flat metrics. These include Schwarzschild, but more generally, they're metrics that are conformal to the Euclidean metric by a harmonic function. So these are still a wide class of metrics to consider, but it is a restriction. The reverse inequality, by the way, requires non-negative scalar curvature globally. Okay. So there's strong evidence that this is a general relativistic mass that's compatible with the ADM mass. You can show that it does give the correct value in Schwarzschild. This also follows from this theorem. It also follows for Schwarzschild from this result of Mantelidis, Miao, and Tam, where they looked at the capacity volume relationship in Schwarzschild space. Okay, so to tie this back in with some of the earlier discussion on low regularity, in the joint work with Perales and Portegies, we defined asymptotically flat local integral current spaces. So they're those same local integral current spaces, but they have to get more and more Euclidean as you go farther out at infinity. Really what we're doing is looking at bi-Lipschitz equivalence to Euclidean space. That gets better and better as you go out to infinity. And then you can generalize this capacity volume mass to those spaces. That's easy to do because you can talk about volume just by using the mass measure, and you can talk about capacity as we were defining it before, where you're minimizing the energy of Lipschitz functions. There's some indication that this capacity volume mass, if you're actually in a weak setting, like a integral current space, it might be nicer to work with than the area volume relationship, the isoparametric mass. One thing is just defining the parameters of sets or the areas of sets. That could be more challenging in the metric space setting. Another reason is just this kind of phenomenon. If you've got some region, this applies even in Euclidean space, not even just metric spaces, but if you have some compact region and you introduce a lot of noise to the boundary, that wreaks havoc on the area. It can make the area huge. You could even make infinite area with a small change, but the capacity is actually stable in that because the capacity is monotone, like the volume, so you can bound it above and below from inside and outside. So the capacity is a more stable object than the area. So that could be useful for working with this in low regularity. Okay. Then just to conclude, just to tie this all together, big picture where the motivation comes from, it's from a couple open problems in general relativity. So one of them is the almost equality case of the positive mass theorem. This is known in a number of cases for intrinsic flat convergence. If you have manifolds whose mass is going to 0, do the spaces have to be converging into Euclidean space in some sense? So that's one well-known open problem. Another one is the Bartnik conjecture, where you're trying to minimize the mass outside of some fixed set. So that's, again, a mass minimization problem. The connection among the low regularity semi-continuity stuff and the general relativity stuff becomes clear once you start talking about this mass minimizing problem. If you're minimizing a quantity, you want to know it's lower semi-continuous. This is work that is done. The most recent results were with Dan Lee, where we showed the ADM mass, isoparametric mass have this lower semi-continuity property that you would want to hold for a mass minimizer. Okay. This is the strongest result is for pointed VF convergence. Both of these problems involve studying mass on non-smooth limits, so that opens the door to considering things like the isoparametric mass, this capacity volume mass. The connection among all of these is that if you use capacity to define mass and you want to know mass is lower semi-continuous, then you would want to know that the capacity is upper semi-continuous. Remember, in the definition of MCV, it uses volume and then capacity with a minus sign. So upper semi-continuity of capacity should correspond to lower semi-continuity of mass. So that's really the connection between those two. It's really part of this broader program of trying to understand low regularity convergence and low regularity spaces for these applications to general relativity. Okay, I think I'm at about time there, so I will go ahead and stop. So thank you.